So this is a simulator that I already uploaded to Blackboard. So after class, if you are interested to play with it, I encourage you to do that. So as you can see here, we have a mass hand as a bottom of a spring system here. And the top of the spring is free, but is subject to an external force. This is the external force or external excitation in terms of displacement or acceleration. So the external force is in red, and the response is in blue. So basically, if we input some harmonic load over here, we can see the response of the mass at the bottom. So over here, we can include any spring constant that you want to use. Right? So for example, here, I believe the minimum number we can put over here is 5. I don't know why it's 5 only. So what mass do you want to use over here? Just keep 1 kilogram over here. Or we can use a different number if you want.
We'll start with 1.
We start with 1.
And we'll
attenuation, so this is for damping. This is for damping. Since tonight we will talk about damping. On damping system, we just keep it at 0. Right? So angular frequency, this is for exciter. So what angular frequency you want to use over here? So now, before we do any input for the external force over here, so now let's see what is the angular frequency for the system here. So we have the k equal to 5, mass equal to 1, the 5 over 1 square root. So the natural frequency, what is the natural frequency of the system?
35. Like 2.
2.236 square root of 5.
$2.236.
2.236.
Okay.
So the frequency of the angular frequency probably we just reduce it to 1, and let's see what will happen here. So we can start here. Remember that when we start the simulation here, and we have the t as the x-axis and then the displacement as the y-axis. The YR, that's the response of the mass at the bottom, and the YE, that's the excitation. So that's the external force or external displacement input, external input. Right? So the red is the input, the blue is the output. So let's see what will happen here. Just stop. Remember that the red color is the input, the blue color is the output. So even we have a sine wave input, the response is not a pure sine wave.
That's kind of all.
Practice 1 and then.
Lowering every time.
Yeah. So after a while, the response goes with a fixed pattern, Let's see. And restart it, as you can see here, at the beginning, and the response does not have a pattern, but after a while, pattern. So that's called the steady state response. Initially, it has some transient response here. And that's where we have the angular frequency equal to 1. Any questions here? Okay. So how about we change the angular frequency for the exciter? What number would you like to use over here? We increase that. Okay. 10. That's great. How about we change it to 2 personally? Yeah, not that much. Change it to 2. Let's see. You see the difference?
And the responses. And then what's that one?
So it's as you can see here, the response is highly dependent on the ratio between the frequency of the input and the frequency of the external force, as well as the frequency of the system itself. Okay. And that's angular frequency equal to 2.
What's making the needle get small go up high?
It's that's because we have the external force that the external force continues in some energy in the system there. So that energy will it's like so how about the remember what is the natural frequency? It's 2.236, right? Would you like to?
Having resonance?
Yes, we will. Let's say what is the resonance here. So online students, are you guys okay? Can you see the animations from your side? Okay, very good. Any questions, or you want to try some frequencies? Please let me know. Okay. So now let's try the 2.236. It's crazy. 2.236. Are you guys excited? What will happen here?
Oh, shit. It's going the other way.
Resonance disaster simulation no longer.
I think disaster's overstating.
Yes. As you can see here, that's yeah.
Now it's also going up.
Yeah. Well, they come out of the screen, and
This is highly entertaining.
it's crazy.
That's like when you take in a wine glass, you make it explode.
So that's 2.236.
Where you attempt to do the.
So this is resonance. And that's a very disastrous obviously. So that means imagine you have a beam there. What is the deformation of that beam?
Oh, it's gonna be bad.
That will be collapse. And that's the. So some of you mentioned they use 10, right? Yeah. Let's try 10. Michelle, sorry, I 10. And some of you mentioned 1,000. And let's say what is. So 10. Let's see what will happen. I love it. It's
And it's also pumping.
So like the motion of the mass is periodic, but it's like a really longer pattern.
Yeah. So as you can see here, if the frequency of the kernel pulse is away from the natural frequency, amplitude is much smaller. Yes.
What if the exciter is a multiple of the natural frequency?
Oh, good question. So
Hunter.
multiple, you mean 2 times?
Yeah.
Okay. Yeah, we can try that. We can try that. So for example, if the exciters frequency is 2 times, 3 times, or 4 times, right? We have 2 times, that's about 4.48, correct? Means steady. So
This isn't exciting as I thought it would be.
that's just regular. Nothing exciting here.
Well, Professor Yang, nothing fancy.
So that's so we have already tested frequency of the exciter smaller than the natural frequency, equal to the natural frequency, larger than the natural frequency. How about we have a frequency much smaller than the natural frequency, such as we have a point 0.1, right?
That doesn't seem exciting.
You will see.
Oh, you.
Interesting, right? So as you can see here, that the frequency of the exciter is very small. So that means the response of the and it will go back.
We're now climbing up.
So it's just following the motion of the exciter.
Yes, very good. Yes. So looks like the response of the system is isolated around the motion of the external force. So looks like the average of the response is pretty much the input over there. Very interesting. Yeah. How about we use 1,000? Some of you suggest 1,000. See what will happen.
To get out more.
1,000. What would you expect if we have a very high frequency for the exciter over here? What would you see?
The red will be pretty even and the blue will go crazy.
So where?
It's personal theory.
So would you see some
Science.
one sine wave or a combination of multiple sine wave or something else? Barrington, what would you expect over here? Yes. Okay, combination of multiple sine waves. So Vishal, Sukan, what?
Many sine waves, but the empty.
Okay, just sine waves. Right? So online students, Hisham, Perry, Patrick, Steve, and Perry, Nick. What would you expect over here if we have a very high frequency for the exciter here? What will be the response here?
Going at this.
Will be one sine wave, a combination of multiple sine waves, or something else here?
Maybe something else.
Well, smart.
I think it's very small sine wave.
Okay, now let's see what will happen.
All right, kids. Oh,
It wouldn't really move. That's
that
what's
kind of
good.
sucks. Oh,
Well, you
wait,
didn't reset it.
hey,
Yeah, it's at
Oh,
10.
that's 10? Oh, that's 10?
Can you
Okay.
not do-
Probably
move a decimal.
probably
Okay.
can't do it.
Ooh, Tim's cheating. Ooh.
Oh, looks like, we are, so it looks like the maximum we can input here is, unfortunately, is,
If you make the spring constant way smaller, I want to have the same.
and then let's try 100 for 3, because, the maximum is 10, so that, we can, other way, we can just, reduce the spring constant or
0.01.
Increase the mass.
increase the mass.
Something has to be 1,000. We're not happy until something.
What's the response here?
It's barely moving.
There's no sine wave.
So Perry, you are correct. There is no sine wave.
Go, Perry.
So that means that if the frequency of exciter is much larger than the natural frequency, so basically, there is no motion for the mass.
It's just no.
So very interesting. Huh? Okay, so let's have a short break and resume the class around 8:40. 45, and let me know if you have any questions during the break. And online students, I would suggest you try the simulator on your side, as it's already uploaded on Blackboard. So let me know if you have any questions.
I can't do classes at the time.
So Nick, you want to put some notes here?
Starbucks.
Yeah.
Why isn't there
But yours doesn't say.
every building?
Yeah, that's.
Okay, guys, ladies and gentlemen, let's start the class, resume the class. In the party. Well, as you can see from the animation we showed before the break, and so the response of the system dependent on a lot of parameters such as natural frequency and the frequency of the external force. So now let's discuss in more details about the some response parameters.
Last name, which is, yeah, I know this building. Yeah.
Oh, you know spelling? Oh, you're good. A lot of people put A right. Instead, and they butcher it.
Now let's look at the
Last name have the.
You got a good memory.
definition of some parameters. So the first parameter that's very important is the static deformation. Static deformation. This is P0 over K equal to U S sub T and U sub S T. This is the static deformation. Makes sense. The amplitude of the force of that spring is equal to static. And This is called static displacement. So, and another one is important is called 1/1 minus beta squared. This parameter is called magnification factor. But actually, this helps.
That equivalent.
And then
P sub O over K. 1/1 minus beta.
just a parameter here. That's it. That's it.
Simple.
And this is so this is used to to evaluate the dynamic amplification fact. This represents amplification.
Something, one of them was the harmonic, what was it? It was the factorial part at the end of.
And another one is RT. It's equal to Q over RT, and that's a function of time, equal to the dynamic response over the static response.
Oh,
The dynamic influence factor. And the beta value. Omega bar over all. Talk about the dynamic responses. Evaluate those 4 parameters. So before the break, we have already actually investigated some special cases. So now let's summarize some special cases. Special cases for the single degree of freedom system under harmonic loading. So, for example, if we have the initial displacement equal to 0, initial velocity equal to 0, so that we should be able to write down the response. So if the initial displacement, the initial velocity, both of them are equal to 0, the response is only dependent on the internal force, so the natural frequency. So we have case 1. If the frequency of the external force much smaller than the actual frequency, that's where we have the So that beta much smaller than 1. So that we can equal to 0, equal to 1. The resultant response, static response times the combination of two sine waves. Right? We have one sine wave with the frequency equal to omega r, another sine wave omega nt. Such as here, if we have the natural frequency is very small, 0.1. If we have this equal to 0.1, as you can see here. That omega bar is much smaller than that. Omega is 2.236. And here, bar is equal to 0.1. So that we will see the response is a combination of two segments. This one. And the case 2, we have, if we have the, I've already tried the case 2. Omega. Omega bar is much larger than omega. So in this case, beta 1 is much larger than 1. Beta. So the amplification factor almost equal to 0. Almost equal to 0. Right? Much larger than 1. So the bottom is close to minus infinite. So approaching to the 0 is approaching to 0. So what would be the UT in this case? UT is equal to 0. So we tried that, remember? Here, if we have this equal to 10,
Thousand.
so the maximum we can put here is 10. So slow. Yeah. I'll refresh it.
Are you sharing two screens?
Yeah. Oh. We use this equal to the mass is 5 equal to 0.1, correct? No.
10.
0.1.
can only go down to one.
This is zero, this is zero. Oh, we should use another number. Oh, this is the case when, yeah, omega bar is much larger than omega, then mass is, the displacement of the mass is about zero. No motion and that's fancy. Yeah. That's one of the most fascinating response. Zero. So case three. If we have the omega or omega n to about equal to one, a lot one. Not one. And if equal to one, that's a resonance here. But if not equal to one, we have the beta. Almost equal to one, almost. So how about the response in this case? Example here, we have, if we have the math, go back to the, where we go. One. Natural angular frequency, if we have the angular frequency equal to not getting. You can see here that amplitude is disaster. So that's resonance. But how about 2 point?
Still a disaster.
Still resonance. Just put 2.1. And it's getting, firstly, it's getting bigger and bigger. Now it's that. Interesting. Then this phenomenon is called peaking. So yeah, if your the frequency of the exciter is close to the network frequency but not equal to, see. So, and you will have a response like you will have a response. You go bigger and bigger as you kind of like this. So So the envelope of the amplitude is pretty much like this. And yeah, it's like or it's like the DNA.
Is that sine of x?
Yeah. So the maximum displacement here. So that's equal to omega n. Beating frequency here. So this phenomenon is called beating.
But not. That's not, but.
It's
Not
almost
one.
equal to 1, but not 80.
It's close
Is
to
that
one,
a
but
2 pi, a negative 2 pi, or a z?
2 times pi. You mean the period of the beating? That's 2 times
Yeah.
pi over omega n minus omega bar.
Okay, thank you.
So that's the beating. So we can have a frequency smaller than that, or we can have a 2 point, for example, 2 point larger than 2.5. Let's say 2.5. We want to have the similar. That's similar.
0.6 or 2.7.
Hunter wants 2 point, the man wants 2.6.
Okay. You may try unlimited numbers after the class. Right? So 2.5 we have the beating here.
Okay.
Either the one was smaller, the one was close to 1, you would have similar. So that's a lot of very confident there. But I would say the response of undamped system is very theoretic, because in the real world, it's very rare to see such type of responses. Imagine if you have a damping there, what will happen? Put a damping number. Yes. So this is a case 3. Case 4, I would say that's the resonance.
Equation for case 3.
No. It's
We should forget.
in the second graph. The equation is here. You have you can just go ahead and use this equation, right?
Oh, and then put in
This equation. So this equation, if you are omega bar, very close to omega, you can plot this function. You can plot this function using Excel. You will see that. But it would be difficult for us to reflect the simple method. So this is the case 3. Any questions? Or if you know any, the next one is the red colors. The case 4. Redlands, no. This is anonymous case 4. Case 4. omega n, omega r equals to omega n. So in this case, particular solution not valid. In this case, p that's equal to so your response particular. Oh, the u should be ut here, c here. So as you can see here, the amplitude is a function of omega e, right? Omega is a constant number. So with the larger time, the amplitude will be larger. So if the time approaching to infinite, the amplitude will be infinite. So that's if you show the will go displacement will be larger, time going. So it's kind of the four special cases we especially that's pretty interesting. So any questions? Are you ready for some examples?
Yes.
Okay. So how about the class with the examples only? How about the class with the exams only?
What?
So now let's see the example here. We have the basically dynamic testing is done here. Right? So we need the mass, the stiffness, and natural frequency of the dot
Was there something like?
system is unknown. So we these properties are to be determined by harmonic excitation test. Basically, that means we adjust the frequency of the internal force. We can use the response of the system under the excitation to determine the mass and the stiffness of the system. So if the force is 4 Hertz, the response tends to increase without bound. It means a resonant condition. So basically here we can tell the natural frequency of the system. Next, if we add some weight here, we will say the resonance occurs at frequency equal to 3 Hertz. see what. So when the frequency of the excitation equal to 4 hertz, we should be able to tell the omega 1 and omega. So when omega bar that's equal to 2 pi times e bar equal. And omega n. Right? What is the relation between omega bar and omega n in this case? You know that at 4 hertz, the resonance recorded is recorded here. What's the natural frequency of the system now? 4 hertz. Yeah, 4 hertz. 4 hertz. So the angular frequency should be equal to. And this should be equal to the initial phase over the initial max. Initial max. So this is the worst case. The same energy and same energy. And when we change the omega bar, the natural frequency, the frequency of excitation is equal to 3 hertz. Then we have the omega bar here, omega bar prime that's equal to 6 times. So we can have that in this case. Same stiffness, where the mass is bigger, Initial mass plus the increased weight over acceleration. Does this make sense? So we have 2 equations here. How many unknown variables here? So K is unknown, M is unknown, where the delta Q and the G is known to us. 2 equations, 2 unknown variables. Solving them should be very straightforward. So solving these 2 equations, we should be able to get the values for K and M. So actually, this example tells us when know the stiffness and the mass of a structure. This is very helpful because in the real world, such as if you would like to know the stiffness of a bridge, it makes sense to do this dynamic testing. Have a exciter on top of the bridge, and then you record the response of the bridge. You can do 2 tests based on the test data. to test there, you should be tell the phase as well as the mass of the bridge over there. Very helpful. So this is different from the static test. For static test, if you would like to know the stiffness of the structure, you need to report the magnitude of the force as well as the magnitude of the deformation. And based on that, you can calculate this. For dynamic test, we just report the frequency of the response there. Similar numbers. So this is a example for undamped system. And how about if we have some damping here? Happen. We have time here. It's also talk about the response of damping system here. This I expect you determine the general solution. Secondary, calculate the amplification factor. This angle. Are to be able to determine the balance damping system. Very similar to the case. I don't have any damping. So how about we have damping? So the equation of motion, and we start from the equation of motion. And this is the beginning of the discovery. Right? What the solution here? Very similar to the undamped system. The full solution would be composed of two parts. We have the general part and the particular part. So the first part is determined by the free vibration. So we have the CT
That the zeta.
Yeah, Rita? Yeah. So we already discussed the response of a version with some damping. So where we have the omega d, that's equal to similarly, we get the particular solution here. Similarly, yes. Particular solution here, that's equal to E1 sine omega t plus 2 cosine omega bar t.
Like assumption.
Yeah, like a assumption. Short y in short y here. So here, similarly, if you work through that, we should be able to here and just gonna skip the math here. So similarly, as we did the revision for the response of undamped system, we should be able to get the response of the damped system here. The particular solution here that's equal to E0 k times space. Say we can just go ahead and this is a cosine omega bar t. Here, that's the same. That's the same as the first term. That's the same both. Or next page, we will simplify this. As you can see here, we have two parts. The first part, so this is amplitude of the sine wave. This is the amplitude of the cosine wave. Amplitudes a little bit different, a little bit different. So if we use beta, beta does the frequency ratio here, and we can simplify this. Yes.
Second half.
Yes, correct. Oh, no, that's not squared. It's not squared. I'm just gonna simplify that in terms of beta under the so the UP. We simplify that equal to so P0 over K, that's equal to UST. Right? UST over the
Before the zeta, the part of the zeta.
that's 2 before the, you know. This is a particular solution, Press that it is. And if you have the textbook, that's the same equation as the textbook. There. So basically, the particular solution here, that's a sine wave. That's a sine wave. If you choose that, do that. And this would be a sine wave. Actually, we can also combine the general solution and the particular solution to get the full solution here. And the full solution could be full solution here, that's equal to 8 times sine. dt, sorry. Sine over dt. Plus the So similarly, we have 2 parts. So this part is called the transient.
That's U sub C.
Pardon me?
That's U sub C.
W's sub so this is a called transient. Because why? If you look at the first term on here, the first term is decreasing with time going, and amplitude is decreasing with time going here. So this part is phased out very quickly, very quickly. And the second part is the amplitude is determined by the second part is called steady state. Steady state response. 2 parts, similarly. So this is a little bit different from on-damped system. This equation is also on your textbook. So if you miss anything here, please double check with your textbook. Last time here. So now let's look at the animation. our favorite friend, our friends. Best friends here, we, regarding damping, we just need to input this attenuation. So the attenuation looks like, that's, function, that the unit is 1/seconds. Looks like the attenuation is pretty much I'm not sure what is correct definition of attenuation here, but we can try it here. So for example, we can input 0.1. Probably that's a damping ratio here. And then let's see what will happen. So we have the 2.5, and we have the lateral frequency, the same as where we have the undamped sampling here. So if we do not have any damping here, we will have beating phenomenon here. But if we have damping here, what will happen? Let's see. It's, we have a little bit beating here, but the phenomenon is reduced by the damping.
So like,
With time going, looks like the beating is phased out. So you can see here, and if we have adequate time to watch the simulation here, as you can see here, if we do not have any damping, we will have beating phenomenon, but we provide some damping here. Looks like eventually the system will have the response will have the same frequency as the external node. Right? In this case, they're all very close, very close. So how about we change the frequency here? We have a smaller frequency here. Usually we have some wind. Then the response, the wave of the response is smooth, approaching to a sine wave. Finally, that's the impact of producing the damping. So satisfying. Yeah. So eventually we have sine wave. So yeah, so we can try some another. another frequency here. Actually, the response is very much the same. We will not have any beat. So how about the resonance in this case? Do you have any resonance? MP here. So let's talk about the response here a little bit over there. So if we show the displacement response function of time, so we will have something like this. So initially we will have some fluctuation initially, but with time going, if we have very long time, so the response will be a sine wave. That's so different from the on-time. Very interesting. So the initial stage we call the the initial stage maybe ends somewhere here. This is called the transient response. Somewhere after a specific time, we have a steady state. Steady state means that shape of the response curve is pretty much a sine wave. So, any questions up to here? So, and now let's see what will happen if we would like to know that. And since the steady state response will be the eventual response of the system here, we response. However, if we just focus on the steady state response, so we can introduce a amplification factor 2 in dynamic. So the transient response can be expressed as a so I would like to simplify this. Have the cosine theta equal to Sin theta equal to. And so that the steady state response can be expressed as the static displacement times d sin theta RD. So the steady state response can be expressed as the shorter form, where the d here, this is dynamic magnification. The theta, this angle. So this is very important. The questions up here, nothing fancy here, just a little bit math. You just express the steady state shorter expression here. So that the dynamic steady displacement can be expressed as dynamic can be expressed as a static response times the dynamic magnification that tells us the magnification of the maximum dynamic displacement compared to the static response times sine term. So where the phase angle tells us the lag between the response and the excitation. So any questions up to here? So so for engineers, we are very interested in the maximum displacement of the system. So the maximum displacement under the excitation here is for the engineers. And the maximum displacement here, that's equal to UST times the US. Yes. So where, as you can see here, D D is only a function of the beta and beta here. The beta is the ratio between the frequencies. Beta is the damping ratio. And the theta The theta can be it also is a function of the damping ratio as well as the frequency ratio over here too. So actually, for damped system, we also have a response called resonance here. The beta responses. And if we plot the amplification factor as a function of beta, some so if damping ratio equal to 0, that is the undamped system. Resonance. So this is theta equal to what? And this is the theta equal to 0.3. This equal to. So for different damping ratios, the amplification factor varies. Actually, the shape varies. Similarly, so this graph is also on your textbook. So similarly, we can plot the theta as a function of we have the ratio equal to 0. Theta equal to 3. Equal to 7. So for different damping ratios, the theta value if here we should so the theta value tells us the in phase or an out phase is what is in phase. In phase that means, for example, so this is if we have the So this is excitation, right? And if we have a response like this is called because the excitation and then the response and signs, and where you may have the outface. This is called the outface. In this case, the input and output we have opposite signs, opposite signs. This is if it's an out. I mean, the theta value tells us information about the direction of the response. For example, if the force in one direction, if this is outface response in the opposite direction. So now this we can try some. So for example, in this case, those number here. 2.5. So if the damping ratio is small, frequency of the excitation is close to the natural frequency. Eventually, we will have the steady state response here. Is this in phase or out phase? And this is out phase because the blue and the red. If the blue is on the peak, the red is heavy. So that's the opposite. This is a out phase, and or we can do the phase difference diagram. This is a out phase. If we increase the damping ratio here, for example, we use 45. Under the damping ratio here, the steady state will occur. Transient response will phase out quickly. Okay. So that's I think that's all tonight, and yeah, you can be able to do more tests over here, and I'm gonna assign homework for you to practice it. Thank you for your time, and see you next time. Any questions from students online?
No, thank you.
Great, thanks.